This video is going to show you the theory behind the Henderson Hasselbach equation, the equation we use to calculate the pH of a weak acid. So when we think about the dissociation of a strong acid, it follows this general formula. HA, where H is the hydrogen and A is the conjugate base pair, fully dissociates, so there's full dissociation, into H plus ions and A minus ions. This could be for any strong acid such as hydrochloric acid, nitric acid, most inorganic acids. However, weak acids only partially dissociate in solution, so instead of having a direct reaction, we get a reverse reaction like so, where only partial dissociation from HA to H plus and conjugate base A minus is taking place. As this reaction is reversible, an equilibrium forms, similar to when we were talking about water in the last video. And as with an equilibrium, the relationship between the concentration of this undissociated acid and the concentration of H plus and A minus ions can be defined by an equilibrium constant. In this instance we call it Ka. So it's defined by the concentration of the reactants on top, such as the concentration of H plus times the concentration of A minus, all over the concentration of the reactant, so in this case, the concentration of HA, the undissociated acid. So here we have the acid dissociation constant defined as an equation, okay? So this is simply just an equilibrium constant for the dissociation of an acid. To investigate pH, we need to isolate the concentration of H plus ions in the equation, because as we know, the pH is defined as the negative log of the concentration of H plus ions. So in order to isolate H plus, what we have to do is times it by the reciprocal of its neighbouring constituents that it's with. So the reciprocal here is HA over A minus. And the reason timesing it by this works to isolate H plus is because we have A minus over A minus, HA over HA, and overall this cancels down to 1, and then 1 times H plus is H plus. However, by the nature of rearranging equations, whatever we do to this side, we must also do to this side, okay? So the left side is also times by HA over A minus. And this gives us our left side of the equation, Ka times HA over A minus. So we have the same equation here, but with a H plus on the left side just for simplicity here. And we want to include pH in our equation. So we know that pH is the negative log of the H plus ion concentration. In order to include pH in this equation, we need to do the negative log of the left side. So negative log of H plus ion concentration is pH. So that's what we have to do. However, as it's an equation, if we do the negative log of the left side, we must also do the negative log of the right side. So by negative logging this whole equation, we get the negative log of H plus is equal to the negative log of Ka and the negative log of HA over A minus from here. So now we need to simplify this quite frankly horrible looking equation that we've got now, okay? So the negative log of H plus is pH. We know that, that's why we did it to the equation, okay? The negative log of Ka is known as pKa, and it's just a constant we achieve when we do the negative log of Ka, okay? We'll talk more about pKa later. So what happens to the negative log of HA over A minus is that it changes to positive log A minus over HA. And the way we do this is we raise it to the power of -1. And you might remember from your logarithm rules, if we raise a log to the power of -1, here we invert the sign in front of it, so it's a positive, and you can flip the fraction. So you have A minus on the top now, and HA at the bottom. So we're left with this equation. pH is equal to pKa plus the log of the conjugate base ion concentration, okay, so that's the proton acceptor, over the concentration of the undissociated acid, which is the proton donor, okay, in acid terms. So this equation is extremely important because it's used to calculate the pH of a weak acid. So before I continue, this equation is really the important thing from this video, to be able to understand how we work out the pH of a weak acid and how we come about finding this equation. That being said, this equation does contain pKa, so it tells us a bit about the role of pKa. Okay? So if we take the example that the concentration of A minus, the concentration of conjugate base, is equal to the concentration of the undissociated acid, then here, when they're in the equation as a division, one over the other, it will equal 1, okay? Because something divided by itself is equal to 1, as they're going to be the same number. This then goes into the equation as the log of 1, and you should know from your logarithm rules that the log of 1 is equal to 0. So if we substitute this back into the equation, it leaves pH is equal to pKa, because the whole of this part is removed. This tells us that pKa is the pH when the concentration of A minus and HA are the same. Okay? So that's just one assumption we can make about pKa based around this equation.